Welcome to the Heartrate Acquisition System with statistical analysis by Avishek. Now the question arises, what is a heartrate monitor or acquisition system? A heartrate monitor system is a personal medical device which allows you to measure your heart rate, or what we call as heartbeats, that is how many times your heart beats in a minute. Heart rate is generally defined in BPM, that is beats per minute. Heart rate refers to the speed of the heartbeat, specifically the number of heartbeats per unit of time. The heart rate is typically expressed as beats per minute. The heart rate can vary according to the body's physical needs, including the need to absorb oxygen and excrete carbon dioxide. Activities that can provoke change include physical exercise, sleep, illness, ingesting, and drugs. The measurement of heart rate is used by medical professionals to assist in the diagnosis and tracking of medical conditions. It is also used by individuals, such as athletes, who are interested in monitoring their heart rate to gain maximum efficiency from their training. Now the question arises, why do you need a heart rate monitor for yourself? Firstly, it improves your health. They can help you find and maintain the right exercise intensity to reach your goals. Secondly, you can measure your effort. Measuring the work rate of the heart is the most accurate method of determining how much benefit you are deriving from your workout, and using a heart rate monitor is more accurate than interrupting your workout to take your pulse manually. Thirdly, it ensures exercise safety. Feedback from heart rate monitor can help prevent you from exercising too hard in a single session and from overtraining in general. Fourthly, you can track your progress. Some monitors are able to store and display weeks' worth of training sessions, which will help you identify possible training errors, or hopefully just reinforce that you are staying on track. And at last, with this you can put the fire back in your program so that you will not ignore your exercise routines to be healthy throughout life. Now we will discuss the bits and pieces of the project. The project is based on the principle of Photoplethysmography, which is a non-invasive optical technique for detecting cardiovascular pulse wave from a fingertip. The heart rate monitor is based on the principle of Photoplethysmography, which is a non-invasive method of measuring the variation in blood volume in tissues using a light source and a detector. Since the change in blood volume is synchronous to the heartbeat, this technique can be used to calculate the heart rate. Transmittance and reflectance are two basic types of photoplethysmography. For the transmittance PPG, a light source is emitted into the tissue and a light detector is placed in the opposite side of the tissue to measure the resultant light. Because of the limited penetration depth of the light through organ tissue, the transmittance PPG is applicable to a restricted body part, such as the finger or the earlobe. However, in the reflectance PPG, the light source and the light detector are both placed on the same side of a body part. The light is emitted into the tissue and the reflected light is measured by the detector. As the light doesn't have to penetrate the body, the reflectance PPG can be applied to any parts of human body. In either case, the detected light reflected from or transmitted through the body part will fluctuate according to the pulsable blood flow caused by the beating of the heart. The whole process is divided into 6 individual block stages, which help us in acquiring the heart rate correctly. The first stage is the infrared optical sensor stage, consisting of an IR transmitter and receiver. The human is required to place his finger onto this module. The second stage is the active low-pass filter stage. The third stage is the amplifier with a gain of 10,000. The fourth stage is the pulse shaper circuit to convert the waves into pure digital waves. The fifth stage is the hero or brain of the project, and that is the Atmel microcontroller-based control circuitry. The sixth and last stage is the display and sound stage. The following picture shows a basic reflectance PPG probe to extract the pulse signal from the fingertip. The subject's finger is illuminated by an infrared light-emitting diode. More or less light is absorbed, depending on the tissue blood volume. Consequently, the reflected light intensity varies with the pulsing of the blood with heartbeat. A plot for this variation against time is referred to via photoplethysmographic or PPG signal. The output from the sensor is a periodic physiological waveform attributed to small variations in the reflected IR light, which is caused by the pulsable tissue blood volume inside the finger. The signal conditioning circuit consists of 2 identical active low-pass filters with a cutoff frequency of about 2.5 Hz. This means the maximum measurable heart rate is about 150 bpm. The operational amplifier IC used in this circuit is LM741, a single-op-amp chip from National Semiconductor. The filtering is necessary to block any higher frequency noises present in the signal. The gain of each filter stage is set to 100, giving the total amplification of about 10000. A 1F capacitor at the input of each stage is required to block the DC component in the signal. The two-stage amplifier and filter provides sufficient gain to boost the weak signal coming from the photosensor unit and convert it into a pulse. An LED connected at the output blinks every time a heartbeat is detected. This is a demonstration of the PPG wave that is obtained out from the previous circuit after amplification and filtering. This is the main circuit that uses the Atmel Atmega 8 as the brain of the project. The 5-volt regulated DC power supply is derived from an unregulated 12-volt input with the help of LM7805 linear voltage regulator and is smoothened using couple of electrolytic and ceramic filter capacitors. This 5-volt rails power the microcontroller and each and every circuit of the project, including the two op-amps discussed in earlier circuit diagram. Two switches are connected to the microcontroller externally pulled up to get start, stop and mode input from the user. Two LED are there to depict the started or stopped state of the measurement process, while 3 more LED are included to tell the user that measurement process is about to begin so that he can firmly place his finger on the sensor to ensure accurate readings. 3 7-segment displays are included in multiplex configuration to display the mode and the result of the measurement. 1 buzzer and a vibrator is also installed with transistor drivers to interact with user. The sensor input from the previous stage is fed to the transistor Q7 to pulsate the circuit and is then fed to 1 pin of the microcontroller to count the pulses. A MAX232 based serial driver circuit is also there to connect aus, reject to the computer. The signal is then converted into digital pulses as shown in the figure down below so that it can be interfaced with the Atmega 8 microcontroller. The microcontroller algorithm counts these pulses and interprets accordingly. The result is then displayed on the 7-segment display and other sound or vibration signals are communicated. The project uses the hardware with the front-end software. Although the hardware is standalone to measure and display the heart rate instantly, it can also be connected to a computer running a Windows application that communicates with the hardware. You can then also save your heartbeat report to the computer's database, analyze it with others' report graphically using animated charts, and can directly take a printout of your heart rate report. The Windows application has been designed using Microsoft Visual Basic 6.0 and the software is fully voice acknowledged. With this project, you can acquire your heart rate instantly, save it to the database, analyze it, and can directly print the report in a matter of seconds, enabling usability and functionality. This is the picture of the finished product. A couple of old telephone DP boxes have been used to build the enclosure for the project and a lot of other raw materials easily available at home. This is the back side of the case. Here is the DC jack for the unregulated 12-volt DC input, a serial port for connecting it to the computer, and the ICSP programming port for the microcontroller programming. Now we will see the demonstration video of the project working as a standalone monitoring system. Let me switch on the device. As you can see the default 15-second mode on the display. I can change it between 15, 30 or 60 seconds mode. 60 seconds mode is the most accurate one. Now I hit the OK button. Now I start the measurement process by pressing start button, and the counting process will start. Now you have to firmly place your finger on the sensor until the process completes. Here it runs for 15 seconds. And the result is displayed. Now we will see the demonstration video of the project working as a monitoring system with computer interface. Here is the software of the project. Open it. Give the password and here is the main GUI. Here you can see the patient name, age, blood group, phone number. The current and date time is also displayed. The patient's heart rate and whether the test is completed is shown here. Here you select the serial port of computer to which your device is connected. Here also you can choose between 15, 30 or 60 seconds mode. We select the 15-second mode and hit the open button to open the serial port. You can also test whether it's present there or not. Now we enter the new patient's data. The name, age, blood group, and the phone number. And click on Save button. Now we will start the measurement. The software asks you to place your finger on the sensor. And here I place my finger on the sensor. And hit OK button. The measurement automatically starts. The progress is also showed. Then it tells you the heart rate result and asks you to save to the computer. I prefer to save it. And the result is saved. Here I can view and compare my report with that of other patients or of other days of measurement. The software has different types of charts to choose from. I can also see the tabular view of the database. I can also directly print my report from here. And here comes the report. I can also print the whole database at once. AVR is obviously the hero of the whole project as because of its fast and robust architecture, easy availability, awesome programming support from third parties and the manufacturer itself, the nice community support, cheaper in cost and yet being powerful, easy to use and deploy in your application, and being the ultimate one for both hobby and industrial purposes and projects. This was just a demonstration prototype of the project. Although fully accomplished and deployable, I plan to develop a more compact and smaller version of it. Next version will be wireless and can be connected to Android gadgets like tablets and smartphones. This unit costs about $8 to $12, however some modifications could be done to bring this unit under $8 price tag. Thank you for your valuable time getting through this project. For more projects, visit my blog at embeddedfortheevil.wordpress.com.